Okay, so there's more than one right answer, of course, here. But here's one example. I think what I was going to do is have you guys draw two examples, but let's just stick with one for now. Here's one answer. And you could actually really draw, I guess, what I had before. But really what matters is that from each of these inputs, from each element in the first set, you could only have one arrow coming out of it. You only have one arrow coming out of it. Okay? So this is one example. Here we have 1 being assigned. It's kind of, and you have to follow the arrows. To 6. 2 is being assigned to 8, as you can see. 3 is being assigned to 2. 4 is being assigned to 4. I should also say here that the range turns out to be everything in Y in these examples. Normally that doesn't have to be the case though. I mean, you could theoretically have elements in Y that are not in the range. Y is where the range lives. Okay, and here's another example. Now this one looks a little weird, I know, right? Because it looks like it wouldn't be a function, right? Because you have everything giving you an output of 2, but this is a function technically. Remember, each element from the first one has to be assigned to a unique element. In other words, each input can only give one output. So 1 is only giving the output of 2. 2 over here is only giving the output of 2. 3 is only giving the output of 2, and so is 4. So in other words, each input has only one output. I mean, they might all be the same, the outputs, but that's fine. You can also see how only one arrow is coming out of each input here. You know, it's not like, let me go back to that other example. It's not like over here. This you can't have. You can't have 2 arrows coming out because now the output is not unique. 1 is assigned not just to one element. 1 is assigned to 2 elements. That you can't have. Well, sorry. Okay, went too far. And also, you can see that the range is just the element 2. So 4, 6, and 8 are not in the range. I like to put this example here because it can be a little confusing at first. That's why I like to put this example in. It clears up that misunderstanding where if everything has the same output, it can't be a function, but it can. Each input can have one output only. Each input can only have one output. Okay, so we have this. Are there any questions so far? Okay. Now, I was going to say, okay, so we have one way to define a function, right? We can use correspondence diagrams. I mean, essentially, to define a function, you have to somehow specify that rule in the definition we saw. Almost like you could think of the rule as like maybe, how do I say this? Like a template that you have to, or yeah, like a template, I guess, you have to adhere to, so to say. You know, your X and Y could be sets. Your rule has to follow the definition. You know, somehow you can only have each element from the first set go to one element from the second set. In other words, each input can only have one output. And the function tells you how to take your input and get the output. For each input, how to get the output. So correspondence diagrams are one way to get a function. Here's another way. We can actually use what's called a relation. And I just put here the definition of what a set is, just to remind you. A relation is another way to get a function. A relation is actually easy. It's just a set of ordered pairs of numbers. That's all a relation is. So these are relations. Now it's just a collection of ordered pairs. And yes, you can actually define a function from these relations. I mean, we'll see later when you actually do get a function. We'll see that a little later. But a relation is just an ordered pair. And yes, there will be a connection to graphing. We will get to that. If not today, then Friday. Let me just say this, that with a relation, you can still consider the domain and range of a relation. Okay, so functions, in other words, are not the only things that can have a domain and a range. Relations can as well. I mean, with a domain, with a relation, the domain is the collection of all the x coordinates, or the first components, as the book calls it. And the range is the collection of all y coordinates, or second components. So for instance, in this relation, I think it's actually one of the ones from, I think it's the same one from the other slide. The domain here would be all these x coordinates. So it would be 1 and 3. We don't list an element more than once in a set. I mean, if you have to do that by mistake with me, I'm not going to mark it wrong. But you really don't want to do that. So here the domain would be 1 and 3. The range would be 4, 2, and 9. So the range would be 4, 2, and 9. And really, we'll see this on the next slide, but let me just say it now. What will end up happening with the relation is that each x coordinate can be assigned to its y coordinate. So each x coordinate is assigned to its y coordinate. So relations, you can have a rule, so to say, but they don't have to be functions, as we're seeing here and we'll see shortly later. So 1, for instance, will be assigned to 4. 1 is also assigned to 2, and 3 is assigned to 9. I mean, we'll see that in the next slide. Let me just finish this one. Here, what would the domain be? Well, it's -2, 0, and 1. All the x coordinates, form the domain. The range is all the y coordinates, 1, 0, and 5. So that's what happens with the range. So with a relation. So with a relation, you can have a domain and range. And with a relation, you are assigning elements from the domain to the range. And that's really what I'm saying here. If you have an ordered pair here, you could think of A as being assigned to B. And because of that, you can actually think of A as being assigned to B, and you could think of forming a correspondence diagram. So with a relation, okay, you have these ordered pairs, you can form a correspondence diagram. And you can actually go the other way as well. In other words, if I gave you a correspondence diagram, right? I gave that to you, okay? What you can do is form a relation out of that. So with the examples from earlier, we can form relations out of those. Namely, if I gave you, you can imagine now the top of the slide here being gone, and I just gave you this correspondence diagram. You can imagine having an ordered pair, A, B, in the relation. You can imagine that. So from here, we can get this, we can get an ordered pair. So there is a connection between relations and order and correspondence diagrams. That's what I'm trying to say. Hopefully I'm being successful, but I think I am. Okay, let me just pause the recording. Let me just pause the recording.